Welcome to today's Explainer, where we're going to explore a really fascinating Stanford engineering seminar. We'll be looking at how combining machine intuition with hard-coded logic is absolutely the key to unlocking general-purpose household robots. I'm super thrilled to guide you through this because, well, if you've ever found yourself wondering why we don't all have personal robot assistants yet, the answers and the solutions being proposed are incredibly cool. We're going to dive into some cutting-edge research from a scientist who transitioned from Amazon to UPenn, proposing an entirely new paradigm for how we build robotic brains.
Okay, let's just dive right into this by comparing how current AI operates with how human intelligence actually works. Right now, to get a robot to do something as incredibly simple as folding a cardboard box, researchers have to literally collect over 100 hours of teleoperation data. Hundreds of hours just to fold a box. Now, compare that to us, to a human. The seminar highlighted this amazing physical trick, using a pen and a bottle cap, one in each hand, to lift a glass off a table without actually touching the glass itself. It's weird, it's kind of awkward, and you've probably never seen it before in your entire life. But as a human, if you see someone do it just once, literally one single example, you immediately get the idea, and you can likely replicate it on the spot.
So we really have to ask, why are today's standard robots failing so completely when you just slightly change their environment or give them a new task? Well, the current standard approach in Silicon Valley is something called data fitting. Basically, you build a giant policy that maps historical observations to the very next action, and you just feed it massive, massive data sets. And sure, it works okay for one highly specific task, but it has terribly low data efficiency and almost zero ability to generalize. If you want a robot to clean a house, where every single home, every object, and every goal is constantly changing, data fitting just isn't going to cut it.
Moving into Section 1, the Neuro-Symbolic Solution.
To solve this massive lack of generalization, researchers are pioneering a brilliant new paradigm. They want to give robots human-like adaptability, stepping away from that brute force data memorization. Instead of getting bogged down in complex jargon, think of neuro-symbolic learning as a marriage of two distinctly human traits. On one side, we have the neural part. This is basically the machine's visual intuition. It spots patterns, shapes, and similarities, much like how you intuitively know how to grab a completely weird object you've never seen before. On the other side, we have the symbolic part. Now think of this as a very strict physics teacher. It understands the hard, unbending rules of geometry, rigid body dynamics, and gravity. By marrying these two concepts together, we get a robot that can intuit and guess what to do, but reliably check its own work before it actually makes a move. And this brilliantly illustrates how the labor is divided in this new paradigm. Just look at this breakdown. The neural network acts as the guesser. It uses AI models to generate possible trajectories or suggest exactly where to grasp an object based on visual similarities from its limited training. But before the robot actually moves a muscle, symbolic planning, which is the checker, takes over. It runs that guess through physical simulators and motion planners. It enforces the rules of physics, prevents the robot from violently colliding with the environment, and ensures the robot's physical joints don't overextend. It's an elegant system of checks and balances. The neural net provides the creative flexibility, and the symbolic planner provides the physical real-world safety.
Which brings us to Section 2, Intuition meets Logic.
Let's see how this actually works in a classic, pretty complex robotics manipulation problem from the seminar, hanging an unfamiliar mug on a mug tree. Imagine you teach a robot to hang a coat hanger on a rack, just once. Now you ask it to hang a coffee mug on a mug tree. The robot has never done this before. Step 1, the neural network looks for a functional correspondence, basically a visual intuition, between the hook of the hanger and the handle of the mug. It guesses, I should probably grab the mug right here. But then, step 2, the symbolic logic steps in and runs a quick simulation. If the neural network simply suggests grabbing the mug by the handle, the symbolic logic says, wait a second, if your massive robotic gripper holds the handle, there's physically no room left to actually slide that handle onto the hook of the mug tree. So it forces a recalculation. It completely rejects the bad guess, prompting the neural net to suggest a new grasp, perhaps on the rim of the mug, so the handle remains free. Finally, step 3, the robot acts, successfully and safely hanging the mug. By replacing dense academic concepts like visual correspondence guidance with the much simpler concept of visual intuition, we can really see the magic happen here. The researchers actually stress-tested this whole system by 3D printing completely random, novel alphabetical shapes, like a giant letter A or B, and telling the robot to hang them on the mug tree. And get this, the system, using this neuro-symbolic intuition and logic, successfully analyzed where to grab and how to hang these bizarre shapes over 90% of the time, all without any prior training data on alphabetical blocks. pure black box AI policies completely, utterly failed this exact same test. All right, moving on to section 3, setting the table with AI. Now, when we scale up to longer, multi-step tasks like setting a dining table based on human instructions, making one good grab just isn't enough anymore. Preparing a meal is a whole sequence of precise interconnected events. If we look at how a purely neural or black box AI tries to set a table, it essentially treats the entire task as one giant mystery to memorize. It tries to map out every object's absolute coordinate based on hundreds of past examples. But the neuro-symbolic system? It uses something called constraint optimization. This simply means breaking down the complex task into a checklist of basic symbolic rules. Rule 1, the apple goes to the left of the plate. Rule 2, the spoon goes to the right. The robot uses large language models to extract this basic common sense knowledge, and then simply searches for a physical layout that satisfies all those small, simple constraints at the exact same time. To actually move the objects to the right spot, the system uses compositional diffusion models. To avoid the really intense math here, just imagine these models acting almost like overlapping magnetic energy fields. Let's say you want to place a cup. Field 1 is a rule saying near the front edge, so it creates a magnetic pole drawing the cup toward the edge of the table. Field 2 is a rule saying to the right of the plate, creating a force pushing the cup in that specific direction. By mathematically overlapping these energy fields, the gradients add up, and the cup naturally slides perfectly into the one specific spot that satisfies all those spatial rules simultaneously. It's a truly beautiful, dynamic way to translate logical rules into smooth physical movement. And that brings us to our final segment, Section 4, the future of smart robots. Zooming out for a second, the speaker makes a wildly compelling case for why this exact framework is the only realistic way we'll ever get helpful robots into our homes. We are actively stepping away from the algorithms of today and looking straight at the intelligent systems of tomorrow. So, the absolute crucial point here is that this system only needs between 1 and 10 demonstrations to learn a completely new capability. That is a magic number, 1 to 10. By combining neural intuition with symbolic physics, we completely bypass the need to collect thousands of hours of data for every unique household layout, every unique plate, and every unique piece of furniture in the world. It finally brings data efficiency down to human levels. Furthermore, the narrator explains that the neuro-symbolic approach solves a massive, massive safety issue. We have got to stop treating AI as a black box. If an end-to-end neural network makes a mistake and smashes a plate on your floor, you have absolutely no idea why it did it. But with a neuro-symbolic system, because the logic is explicitly hard-coded, scientists can truly understand how hard a task is. They can open up the system and verify exactly why a robot made a specific choice. Ah, okay, it thought the cup was blocked by the bowl over here. Rather than blindly trusting a massive, completely unreadable AI model to operate around your family and your living room. This all leads to the ultimate holy grail of robotics, continual learning. Because the robot can safely verify its own actions using symbolic logic, like running an internal simulation to check if placing a book on a shelf will accidentally knock over a clock sitting right next to it, it doesn't constantly need a human holding its hand to prevent disasters. It can start with basic capabilities, explore its environment totally safely, figure out novel tasks on its own, and actually self-improve autonomously. It effectively generates its own safe training data. As the speaker perfectly captures in this quote from the seminar, I would argue what we want for robotics is some system that can learn from very few demonstrations and being able to generalize across different kinds of scenarios. This is the entire driving philosophy of the research. We are moving away from rigid, fragile data-fitting algorithms and moving toward machines that can finally adapt to our messy, unpredictable, and wonderfully complex lives. It's truly incredible to imagine how this neurosymbolic synthesis is going to transform our daily lives. By blending the flexible intuition of a neural network with the unbending logic of physics, we are finally closing in on general-purpose physical intelligence. It leaves us to wonder, once these robots enter our homes, and once you can effortlessly teach your future robotic companion to cook your absolute favorite meal from just one single demonstration, what on earth will you teach it next? Thanks so much for joining me on this explainer. Keep learning, and I'll see you next time.